Hi, so now we need to talk about binomial distributions. Now this is a specific kind of discrete distribution, just like we've been talking about. And we could create a table for these values, just like we did before. The difference is that the binomial distribution covers a specific process, a specific scenario that we'll talk about in just a minute. But the probabilities, instead of just being given to you, are calculated from a formula. All right, and we talk about this distribution because later on in the course we need it in order to make inferences about proportions. So that's why we're doing this. So let me give you an example of a process that's binomial. And by the way, binomial, if you pick apart that word, stands for two names. Okay, two names. So the binomial distribution deals with scenarios where we have outcomes that belong to two categories, like something that is acceptable versus defective, or a plant that survived or died. We usually refer to those as a success or failure. Okay, so the two categories are usually success and failure. However we define those. And that's of course not a value judgment, just whatever we're counting. So an example of a binomial process would be if we take a fair coin, and a fair coin means that it has 50-50 chance of landing on heads or tails, and we flip it 20 times. And we count how many of those times it lands on heads. The number of times it lands on heads would represent x, and then the probabilities associated with different values of x would be p of x. So let's pick that apart a little more. So the first requirement is that we have a fixed number of trials. Okay, and in this scenario, each trial is the flipping of a coin. Okay, so we've got 20 trials. That's a fixed number. We decided in advance it's going to be 20. Okay, so the notation for number of trials is n. So here n equals 20. The trials have to be independent. What that means is if I flip a heads on the third flip, does that change the probability of getting a heads on the fourth flip? No. It doesn't matter how many heads I flip in a row, the probability that the next one is heads is still going to be 50-50. So that's what it means to be independent. The third one, each trial must have all outcomes classified into two categories, which we refer to as success and failure, like we talked about before. So in this case, since we're counting number of heads would be considered a success. And then finally, the probability of success remains the same across all trials. That probability is p. So p equals 0.5 in our scenario of flipping a coin. Okay, and that probability stays the same no matter what. So just to review notation, n is the number of trials, x is the number of successes out of n trials, lowercase p is the probability of success in any one of the trials. Q, I don't really use Q, but your book just uses Q as basically just 1 minus P. 1 minus P is just the probability of failure. And then P of X is the probability of getting X successes in the N trials. So to start with an example, let's see if this is binomial or not. If we select a random adult, suppose we know there's an 85% chance that this person has heard of Twitter. And then we want to find the probability that if we select 5 people, that exactly 3 of those adults have heard of Twitter. So the question is this binomial? Well, yes, so we've got 5 trials, so that's fixed 5 trials. They're independent. So if we pick one person and they know what Twitter is, that doesn't impact what the next person says. So we've got each trial having 2 outcomes, whether they do or don't know what Twitter is. And then there's a constant probability of 85% across all trials. So therefore, that's a binomial random variable. Okay. The other thing, just to help make it clear, what we're looking for here is the probability of how many of the trials are a success. Okay, so in this case, we want probability that x equals 3. Okay, so another example. Suppose we found out that for pregnancies that occur with the aid of fertility drugs, 1/3 of them result in multiple births. So if we took a sample of 10 pregnancies, different couples, what's the probability that between 2 and 4, including 2 and 4, would result in multiples? So does this result in binomial distribution? Yes. We've got 10 trials. The trials are independent. That's why it's important that we said they're from different couples. If we had pregnancies from the same couples, that might not be independent. Each trial has 2 outcomes. The first outcome is multiple birth. The second one is not multiple birth. And then the probability is always 1/3 that the pregnancy would result in multiples. And then we're counting how many of the 10 would result in multiples. So that's going to be a binomial. So things to look out for. So you might not have a fixed number of trials. So if you did, it wouldn't be binomial. So if you're going to keep repeating the process until you get 50 heads, then that's not going to be binomial. So the second thing, if you've got something that's not independent, so if you're looking at the probability that it rains, that's not going to have a constant probability, because the weather today partly depends on the weather yesterday. Or if you're sampling without replacement, meaning you're sampling something and then not putting it back, like from a deck of cards. If we sample a card and then don't put it back in the deck and shuffle, that's sampling without replacement. That's not going to be binomial. The third is non-constant probability. Occasionally you'll have a process that's, for some reason, the probability changes over time. And I can't even come up with a good example other than independence. So just look out for that. All right, so the first example we talked about with the whether adults know what Twitter is. I'm not going to ask you to find the probabilities by hand. I'm going to let you use StatCrunch for that. And you can see there's a separate video showing you how to find this probability. So that probability that x equals 3, came out to be 0.1382. Okay, we had 5 trials. N was 5. P was 0.85 because that was our probability of success in any one given trial. So the probability that exactly 3 out of the 5 knew what Twitter was would be 0.1382. For the second example, if we wanted to know the probability that between 2 and 4 inclusive of the 10 pregnancies would result in multiples, our N was 10, our P was 1/3, so 0.3333. And then we have between 2 and 4. And that gave us a probability of 0.6829. Okay, so I'm letting you do these in StatCrunch. The formula is pretty nasty, so we'll just go straight there. A third example, this is a new one. If you're taking a 10-question multiple choice test, and there are 4 choices per question, A through D, and suppose it's written in some language you've never heard of before, and all you can do is randomly guess. What's the probability that you'd pass with a C or better? Well, a C would be 70%, so you need 7 questions to pass with a C or better. So we've got 10 trials, because there are 10 questions. Probability of success on each one would be 0.25. And so we'd want the probability that P would be greater than or equal to 7. That comes out to be 0.0035. So according to the rare event rule, that would be very, very rare. And students always think they want multiple choice tests, but maybe this will help convince you that they're not as great as you thought. All right, so next we need to do the mean and standard deviation. These are just formulas. So the mean, this formula is for the mean of a binomial distribution. Okay, so mu is just n times p. The variance, again, sigma squared, is just n times p times 1 minus p. And then to get the standard deviation, you just take the square root of that. So if we look at the example for the multiple choice test, the mean would be number of trials, which is 10, times probability of success, so 0.25. So on average, you'd expect to get 2.5 questions correct out of the 10. So the variance then is going to be n, which is 10, times 0.25, times 1 minus p, so times 1 minus 0.25. So the variance is 1.875. And then to get the standard deviation, you just take the square root of 1.875 and get 1.3693. All right, so that's it.